All right, let's go ahead and finish up 2.6 here. So, what we're going to do here, and this is something that you should practice and be good at doing, and it's basically figuring out, a function that fits the given properties. So, let's go ahead and try and go through and do it, and I'm going to try and color code this sum. So, let's look first at f of 0 equals 0. Now, one of the things you need to remember before I get into this too much is that the answers here are not unique. They are not unique. So you may not always come up with the exact same graph as everybody else because you could come up with multiple graphs that have these same properties. All right, so let's start by looking at f of x equals 0, and that's just going to tell us that we have to go through that point right there. F of x equals 0. The next one tells us f of 1 equals 2. And I'll do that here in this pink color. So f of 1 equals 2. So if we go to 1, 2, that's the point 1, 2 right there. Our graph has to go through that point. The next one tells us that f of negative 1 equals negative 2. Okay, that's this right here. F of negative 1 equals negative 2. And so that's that point right there. So now we have to go through these 3 points. Then it also goes on to tell us that the limit of f of x as x goes to negative infinity is negative 1. So that means that as we go to negative infinity, let me get, let's just do it by hand here. That as we go to negative infinity, we have to approach this line right there. Okay, that's the negative 1 line. And then finally, as x goes to infinity, the graph has to go to x equals 1, which is this horizontal line right here. Okay, so that's where we have to go. So then we have to draw in some sort of function that fits that. And so I would say, all right, we start here, we have to go up, need to go through that point, and then I'm going to say, all right, it curves back down and then approaches infinity as we go that way. And then I'm going to do the same thing down here, and it'll approach infinity that way. So something like that, that would work, and that would be an acceptable graph. Is that the only graph that I could have drawn? No, I mean, I could have done something that went up like this and did something like this or something. Like I could have done anything I wanted as long as it fit those properties, then we'd be good. So I'm going to leave it with that one, and that is that's the actual graph right there. So I'm going to darken that line in just a little bit, just so you can see it better. There's the actual graph, and I color-coded the properties there that we're matching. Okay, so take a look through that, practice it, make sure you can do that kind of thing, just looking at the given properties and limits. All right, next, oblique asymptotes. So consider the function f of x equals x squared minus 3 over 2x minus 4. Here, we can take the limit as x goes to infinity of x squared minus 3 over 2x minus 4. And when we take that limit, it goes to infinity because our numerator is greater than our denominator, and therefore it's going to blow up very fast. And then if we take a look at the limit as x goes to negative infinity of x squared minus 3 over 2x minus 4, this one's going to go to negative infinity. We end up with x, basically we have an x over, we end up with x squared over x, which is just an x, which means this is just going to go to, this is just going to go to, it's going to go to negative infinity because that's how our x graphs are shaped. They're like that. Remember the odd ones, the odd functions, x cubes, x to the fifths and stuff like that, they go to negative infinity as you go to negative infinity and go to positive infinity as you go to positive infinity. Unlike the even polynomials, which do stuff like that, where they both go to infinities as you go to infinities, assuming there's no negative signs out in front of them. So how do we get that? Well, if you look at x squared minus 3 over 2x minus 4, it can actually be rewritten as this function right here. You can break it apart like that, and you end up with x over 2 plus 1 plus 1 over 2x minus 4. So basically you just do the division out, and this is what you'd get. And so if we look at this first part, we'd have, if we take the limit as x goes to infinity, that first part is just going to go to infinity. This is just x. It just blows up. That goes to infinity. So it's like infinity plus 1, which is just infinity. And then this part over here, that's just going to go to 0 because it's a 1 over x. And so that's what we end up with, is this part over here, as we go to infinity, doesn't really actually do anything. But this part over here, right here, this part, is really very dominant, and it is actually the line x over 2 plus 1, right? That's just a y equals mx plus b. It's like a 1/2 x plus 1, slope of 1/2, y-intercept of 1. And you can see that line right here drawn in. See it right here? Right there. Drawn in on the graph. I went over it in black here, but it's right here. This is it on the graph. It's this x over 2 plus 1, or 1/2 x plus 1, and that is your oblique asymptote. Okay? So if you don't remember doing that from before, there's a quick little lesson for it on you. Basically, as you zoom really, really, really far out, you can look at that graph, right? That's my 1/2, my x over 2 plus 1. That's that line there. And then your other graph is basically going to look like this, where right at 2, it's going to do something like that. And then it's just going to curve up and go right along this other line and follow it. And then from down below, it's going to come straight on up here like that. And then it's just going to curve over. And so really, if you zoom way out, only right here does it look different. Everywhere else, it's going to look like x over 2 plus 1. Here, summary of the rational functions. Now, I did this earlier, so what I'll do just to help keep it simple is go back over here. Where did I write that? Right there. I'll grab this, I will copy it, and I'll put it back over there. But these are our 3 situations here. So I just didn't want to go on from that point without having gone over it. So I gave it to you a little earlier. So we'll paste that in. There you go. Here are the 3 cases for what we've got there. So we already did that. Here, infinite limits. These are used to describe vertical asymptotes. Okay, so consider the following limits. The limit as x goes to 0 from the plus side here on this graph. If we look here, we're blowing up to infinity as we do that of 1 over x, and so this is going to be infinity it goes to. The limit as x goes to 0 from the negative side, that's down here as we blow up down toward negative infinity. And then the limit as x goes to 0 here, it does not exist because the left and right limits do not match. So what can be said? What we can say is that there's a vertical asymptote. We can say that there's a vertical asymptote at x equals 0. That's what we can say about that. Okay? So now let's discuss the behavior of f of x as 1 over x squared as x goes to 0. So here, if we look at the same things, the limit as x goes to 0 from the plus side of 1 over x squared, here, that's going to also be infinity, or blowing up to infinity like that. And if we look at the limit as x goes to 0 from the left side, from the minus side of 1 over x squared, that's going to also be infinity, because here it's all going positive, so we're blowing up to positive infinity there. That means the limit as x goes to 0 of 1 over x squared is also just infinity. Those two things, the other left and right limits match, therefore it's infinity. And so while the limit as x goes to 0, the function values become infinite. Okay? So No matter how high of a number you pick, it's always going to be better. So techniques for finding these limits. Let's take a look at the limit as x goes to 1 from the left side of 1 over x minus 1. So here, let's take a look at A. We're going to have a vertical asymptote at x equals 1. And so we'll look at this and do limit as x goes to 1 plus. And what we've got is 1 over x minus 1. And if we're plugging in positive numbers, then the top stays positive. So basically, like, we have a positive, and the bottom, if we plug in positive numbers, is going to be positive because we're coming from the positive side. So we have numbers slightly greater than 1. So a number slightly greater than 1 minus 1 is a positive number, which gives us a plus over plus, which gives us an infinity. And if you wanted, you could think about this as like 1 over 1.1 minus 1, and that's 1 over 0.1. And then you could do 1 over 1.01 minus 1. That's 1 over 0.01. And, you know, as our x value gets closer and closer to 1, that denominator gets smaller and smaller, and so therefore this blows up to infinity. All right, taking a look at B, what about the limit as x goes to 1 from the minus side? Here we end up with 1 over x minus 1, but this time we're looking at x values that are close to 1 but less than 1. And so what's going to happen is we're going to have something slightly smaller than 1 minus 1. That gives us a negative number, and then the top stays positive, and so that's going to just equal negative infinity. And you could do the same sort of thing. Look at 1 over 0.9 minus 1. All right, and 1 over 0.09 minus 1, and 1, you know, so on and so forth. And see what those values do, and you'll see that the denominator gets smaller and smaller, but it also gets smaller and smaller in the negative direction. So we're just looking at the sign of the top and the signs of the bottom to decide if it goes to positive or negative infinity. Here are some examples. I'd let you try those, and I'll fill them out for you in the notes so that you can have them to look at. And the same thing on this page. Try those again, looking at what happens, and I'll put them for you in the notes to look at. And I guess one more page of that. Is that the same as the last page? It's the same as the last page, isn't it? Oh no, those are just as it goes to 2. So take a look at all those, and I'll put them in the notes for you. All right, precise definition of infinite limits. We say that f of x approaches infinity as x approaches x naught, and write the limit as x goes to x naught of f of x equals infinity if for every positive real number b there exists a corresponding delta such that for all x minus x naught absolute values between 0 and delta, and this then implies that f of x is greater than b. And then similarly for the negative infinity, and you can see it there in the graphs, that basically we just keep going bigger and bigger and bigger no matter what value you pick. We can do that. All right, so vertical asymptotes definition. A line x equals a is a vertical asymptote of the graph of a function y equals f of x if either the limit as x goes to a from the plus side goes to plus or minus infinity, or the limit as x goes to negative a from the negative side of f of x is plus or minus infinity. So if either the left or right limit goes to positive or negative infinity, we're going to say we have a vertical asymptote. So graph the function f of x equals negative 8 over x squared minus 4 using asymptotes. And so first off, we're going to look and see if there's any symmetry. So let's look at, is it odd or even? So we do f of x, and we do it with f of negative x. This becomes negative, and we'll have 8 over negative x squared minus 4, which is just going to be negative 8 over x squared minus 4, which just equals our original function. That means that this is an even function. So we have even symmetry here. So to find the horizontal asymptote, and remember, if it's an even function, it means it mirror images across the y-axis. So to find the horizontal asymptotes, we are interested in the behavior as x goes to plus or minus infinity, right? And as x goes to plus or minus infinity, you can look here and see what happens. As x goes to positive infinity, right, as the limit as x goes to infinity here, we have negative 8 over x squared minus 4. Well, as x goes to infinity, the denominator goes to infinity. This goes to 0. And then the same thing as limit as x goes to negative infinity. Again, the denominator goes to infinity, and so it's 1 over, or something small 8 divided by something huge infinity. It's going to 0. And then last here, to find the vertical asymptotes, we are interested in the behavior as y goes to plus or minus infinity. And so you go through to do that, and then you can actually graph it. And so what I will do is I'm going to let you have a look at this last little part here, what the vertical asymptotes are, and then on the next page you can go through and draw it out and see what you think it's going to look like for that graph. And then, try it and see, and look and see if you've got it right. I'll also draw it in and finish this up in the notes so you compare it to, but see how close you can get just by thinking of these how close you can get of a picture just by looking at this part right here. Okay. Last, just some little examples you can take a look at of some some vertical asymptotes and things like that. Here you have a horizontal asymptote, but when you remember, the inverse function of e to the x is natural log of x, we end up a horizontal asymptote becomes a vertical asymptote there. And then here, secant and tangent, you can look and see they have vertical asymptotes in those graphs. And you can take a look at that. And then here, lastly, try looking at the graphs of these and determining these things. All right. So take a look at those, and I'll write these again as answers in there. But try to remember the graphs of these real quick. I don't really want to do them, but remember they're similar to these two, not exactly. And see if you can figure out by sketching out the graph what these two limits are. And again, I'll put them in the notes, and I'm happy to answer your questions on them in class if you need it. All right, that's all.